New pictures obtained by the James Webb Space Telescope have stunned researchers. Rather than expanding our perception of the universe, these pictures revealed a disturbing reality. Our current understanding is lacking, and we struggle to grasp the full scope of the universe in its early stages. The hypothesis regarding the universe's origin is now being pushed to its limits, prompting new theories about its formation. The central question arises: how was the universe formed, and why does this discovery challenge even the most experienced space specialists in understanding the Big Bang and its ongoing complexities? This leads us to assess the Big Bang theory itself. Contrary to popular belief, the Big Bang was not an explosion within pre-existing space. Rather, it was space itself that began around 13.8 billion years ago, along with matter and time. This idea is based on a remarkable characteristic in physical science and cosmology: a singularity, where gravity is so strong that space-time curvature becomes infinite. Today, after billions of years since the beginning of the universe, we understand that our celestial home is part of a significant cooperation. For experts, this reveals an essential part of the universe's existence. Its continuous development shows that the universe is not moving through pre-existing space, but rather that space itself is constantly expanding. According to conventional theories, the first stars began to shine between 200 and 300 million years after the Big Bang, marking the end of the so-called Dark Age. This was when the first radiant celestial objects clustered together to form mature galaxies. However, the speed at which these early galaxies developed remains an ongoing mystery. A major piece of data emerged from the first images captured by the James Webb Space Telescope in July 2022. Experts announced that the telescope had detected various galaxies, some of which existed only about 300 million years after the formation of the universe. Compared to the galaxies that formed billions of years later, these early galaxies were considerably smaller and less massive, which fit well with the scientific model. The density of matter in the early universe was simply not enough to form galaxies the size of those we observe today. However, the discovery of 6 amazing redshifted light spots from the James Webb Telescope triggered one of the most significant astronomical crises in recent times. These newly discovered galaxies, though similar in age to previously recorded worlds, are nearly as massive as our own Milky Way galaxy. This raises an intriguing mystery in cosmology. By examining a series of images taken by the near-infrared camera, experts identified the light sources. Using redshift, they confirmed that the light from these objects took more than 1 billion years to reach us, indicating these galaxies formed between 570 and 700 million years after the confirmed Big Bang. Strikingly, these galaxies were so large that they defied conventional cosmological assumptions. Instead of finding the expected dwarf galaxies, the structures identified were almost as large as the Milky Way. Upon further analysis, experts concluded that these galaxies were already gravitationally bound collections of stars with masses exceeding 10 billion times that of the Sun. One of these might even be as massive as 10 billion solar masses. However, whether this possibility is true, the mystery remains unresolved. Even in this scenario, there would be much more mass in the early universe than previously anticipated, introducing a riddle to our understanding. These objects challenge nearly all conventional cosmological theories. If even one of these galaxies turns out to be real, it would significantly challenge past assumptions about the formation of early galaxies. Moreover, the density of matter in the early universe would need to be several times greater than previously accepted to explain this phenomenon. One alternative explanation suggests that these galaxies formed in a completely unknown manner, further complicating the cosmological picture. These discoveries and the resulting discussions are likely to lead to further examination of the Big Bang theory. Many space experts, especially those with alternative viewpoints, are frustrated and often find their perspectives disregarded in scientific journals. Even those who express doubts about existing hypotheses are frequently labeled as unconventional or peculiar. However, it is clear that even experts who still defend the Big Bang theory are continually confronted with questions that remain unanswered. These inquiries include why and how, 13.8 billion years ago, something literally arose from nothing. Could something really have started from nothing? Or was there some triggering event? Was it all just a mishap? Stephen Hawking pointed out that the nature of time as we know it began with the Big Bang. Therefore, this process could not have been set off by an external cause. A similar ambiguous question involves the consistency of radiation and matter distribution throughout the universe. Regardless of which direction or at what distance we look, on a larger cosmic scale, we find similar densities and distributions of galaxies, nebulae, and radiation. Modern theorists explain this phenomenon with the theory of cosmic inflation. However, some experts have extended this assumption with the theory of turbulent inflation, suggesting that inflation has only stopped in certain regions like bubbles, continuing incomprehensibly in others. This leads to the possibility of multiple universes forming in these bubbles, each governed by its own physical laws. In this model, a big question arises: what if our universe doesn't represent the total whole? What if another universe existed before our own? In this case, the Big Bang could be part of a larger cyclical pattern. Our universe would then be a part of a greater, more complex structure. According to this view, there could be an eternal pattern of collapse and rebirth. However, this is not the only perspective in cosmology. For example, an article published in 1955 by NASA's Big Time suggested that the universe might never have experienced a Big Bang, and instead it may have existed for an indefinite period. In this view, the expansion of the universe would be non-existent, and the continuous improvement of matter could give the illusion of constant growth. Another intriguing and controversial theory emerges from quantum physics and string theory. Some experiments suggest that our universe, and everything within it, may be a projection or a higher dimensional simulation. While this may sound like the premise of a science fiction film, it could be linked to the Kessler scale, which measures a civilization's ability to harness energy. If a Type 3 civilization were capable of utilizing the energy of an entire galaxy, it might create a perfect simulation. However, confirming the reality of such a theory is deeply complex and speculative. Exploring the depths of cosmology and the origins of our universe leads us into profound mystery and ongoing scientific inquiry. The new images captured by the James Webb Space Telescope have reignited debates about the very fabric of reality, challenging established hypotheses and prompting scientists to reconsider fundamental aspects of cosmological understanding. At the core of this inquiry lies the theory of the universe's origin, a cornerstone of modern cosmology. According to this theory, approximately 13.8 billion years ago, the universe emerged from an extraordinarily dense and hot state, expanding rapidly to form the space-time and matter we know today. This colossal event wasn't just an explosion within pre-existing space, but rather the beginning of space itself. The notion of a singularity, where gravitational forces are so intense that space-time curvature becomes infinite, supports our understanding of this early cosmic epoch. However, the discovery of early galaxies by the James Webb Telescope challenges our assumptions about how rapidly structure formed in the universe's infancy. These galaxies, detected just a few 100 million years after the Big Bang, are surprisingly developed and massive compared to current cosmological models. One of the key questions raised by these discoveries is the nature of cosmic inflation. According to the prevailing theory, inflation occurred in fractions of a second after the Big Bang, causing the universe to expand drastically. This rapid expansion explains the uniformity of cosmic microwave background radiation observed across the universe today. However, the current discoveries suggest complications in the early universe's development, which may require adjustments to inflationary models. The formation of galaxies like those observed by the James Webb Telescope forces cosmologists to reconsider the conditions and processes governing the universe's early history. These galaxies, large and massive so soon after the Big Bang, suggest that the density of matter was much higher than previously estimated. The mystery deepens when we consider how such massive structures could form and evolve in such a short period. Additionally, the discovery of these galaxies raises questions about dark matter and dark energy, two elusive components that make up most of the universe's mass and energy content. While dark matter is believed to provide the gravitational framework necessary for galaxy formation, the distribution and properties of dark matter in the early universe remain uncertain. In line with these astrophysical mysteries, theoretical physicists are exploring alternative cosmological models that challenge the standard Big Bang perspective. Some theories suggest that our universe is only one of many in a vast multiverse, each with its own physical laws and constants. These ideas, emerging from advancements in string theory and quantum cosmology, propose a more interconnected universe than previously imagined. One theory gaining traction is eternal inflation, where universes constantly emerge from a larger inflating space. This theory suggests that our universe is just one bubble among countless others, each with its own set of physical properties. The challenge lies in finding observable evidence to support such speculative ideas, as they push the boundaries of observational validation. Another provocative theory posits that our universe exists within a simulated reality, much like a computer-generated recreation. This concept draws parallels to advancements in artificial intelligence and computational science, where simulations can mimic complex systems. If true, our perception of reality as a distinct physical universe could be fundamentally altered, raising significant philosophical and scientific questions about the nature of existence. Further advancements in observational astronomy continue to reveal the vastness and complexity of the universe. Telescopes like the James Webb Space Telescope, with its remarkable sensitivity and resolution, promise to uncover even more secrets of the universe. Future observations may shed light on the earliest moments of the universe, offering clues to its ultimate fate and the fundamental principles governing its evolution. Beyond observational astronomy, particle physicists are investigating the fundamental particles and forces that shape the universe. The quest to unify gravity with the other three fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, remains a central goal of theoretical physics. Models like quantum gravity and string theory offer potential frameworks for understanding these interactions at both the smallest and largest scales. In the realm of quantum mechanics, the nature of time itself remains a subject of intense debate. Quantum theories suggest that time may be evolving or even elusive at the most fundamental level. Understanding the nature of time within the context of cosmological models could reshape our understanding of the universe's beginnings and evolution. Additionally, the search for extraterrestrial life continues to captivate the public imagination and drive scientific inquiry. The discovery of exoplanets, planets orbiting stars outside our solar system, has expanded our understanding of planetary diversity and the potential for habitable environments elsewhere in the universe. Future missions, such as the James Webb Space Telescope's investigation of exoplanet atmospheres, may provide evidence of biosignatures indicative of life beyond Earth. In addition to these scientific pursuits, cultural and philosophical reflections on the universe enhance our understanding of our place within it. Questions about the meaning of existence, the possibility of intelligent life elsewhere, and humanity's future in space exploration continue to drive research and debate across disciplines. As researchers delve deeper into the implications of the James Webb Space Telescope's discoveries, the quest for understanding the universe's origins only grows more complex. The newly detected early galaxies challenge not only our assumptions about the timeline of cosmic events but also how we view the entire formation of structures in the universe. These discoveries suggest that galaxies may have evolved in ways that are inconsistent with traditional cosmological models, pushing the boundaries of how we comprehend star formation, the growth of galaxies, and the role of dark matter. The mystery deepens as scientists try to reconcile these observations with current understanding of the processes that governed the earliest epochs of the universe. In particular, the notion that galaxies could be as massive as the Milky Way within just a few 100 million years after the Big Bang raises questions about the role of dark matter in accelerating galaxy formation. If the galaxies formed with such rapidity, the assumptions about dark matter's influence and distribution in the early universe may need to be re-examined. Beyond dark matter, dark energy, the enigmatic force driving the accelerated expansion of the universe, also faces scrutiny. While cosmologists have long thought that dark energy plays a crucial role in the universe's expansion, the possibility of faster galaxy formation hints that dark energy may have had a different impact on the early universe than previously believed. These new discoveries are forcing scientists to rethink the entire structure of cosmic evolution, suggesting that our understanding of the interaction between dark matter, dark energy, and regular matter may be incomplete. One of the most profound implications of these discoveries concerns the very nature of space itself. The rapid expansion of the universe in the aftermath of the Big Bang, as theorized by the inflation model, suggested that the universe underwent an almost instantaneous expansion from a singularity. However, The findings from the James Webb Space Telescope seem to challenge this narrative, suggesting that the rate of expansion in the early universe may not have been uniform across all regions. This could lead to new models of cosmic inflation, proposing that certain parts of the universe may have inflated differently, leading to the formation of structures that are much more massive and developed than expected. In addition to questioning the fundamentals of cosmology, the discoveries by the James Webb Space Telescope also open new avenues for considering the future of the universe. As these galaxies appear more advanced than anticipated, the possibility of the universe undergoing similar stages of development on a larger scale becomes intriguing. Could the universe itself be reaching a stage where it might start to exhibit signs of maturity, where the rapid formation of cosmic structures could eventually slow down? These questions will drive further investigations into the rate of cosmic expansion and whether the universe is heading toward a new phase. Moreover, the increasing precision of tools like the James Webb Space Telescope may not only help us understand the evolution of galaxies, but also provide new insights into the chemical compositions of distant stars and exoplanets. By analyzing the atmospheres of exoplanets, scientists could one day detect biosignatures or other indicators of life beyond Earth, a discovery that would dramatically alter our understanding of life's potential elsewhere in the cosmos. The future of space exploration, spurred by these revelations, could lead to a new era of scientific exploration where the boundaries of what we know are constantly expanding, unraveling new mysteries about the universe's vast and complex nature.